All right, let's do this, shall we? Yes, we shall. So we're talking about the nuclear energy generation rate, or reaction rates, and remember we use epsilon to mean the energy generated per kilogram per second within stellar material. That could be because of gravitational contraction or even expansion, in which case would be negative. Concentrating on nuclear reactions, and so epsilon is defined to be how much energy is generated per kilogram per second, and we said, well, that'll be the sum of how much available energy is generated per reaction step. We're summing over all the reaction steps, the steps in the sequence. Available energy generated in a given reaction step times how many reactions of that step are happening per cubic meter per second, but we want all this per kilogram, and so we have to multiply by the number of cubic meters in a kilogram, cancel out those cubic meters there, and of course the number of cubic meters per kilogram is just the reciprocal of the number of kilograms per cubic meter, which is just the density. So that would, in other words, dividing by the density is that last term there. And we were talking about how the second term here has to be the same for all the reaction steps in a sequence at equilibrium. And so then we mentioned that, for example, and equilibrium means that the concentrations, the number of reactants per cubic meter are essentially staying the same. Nothing is building up, nothing is depleting. And again, it's been days and days, so I just want to remind you of all of this, because otherwise you might lose the thread. So the example we gave is that, remember that in the proton-proton chain, that we have a step where a deuterium nucleus and a proton collide, and that produces a helium-3 nucleus. And then the last step is that helium-3 nuclei can combine with one another to make helium-4 plus a pair of protons. And so if this weren't true, that everything was, that the number of reactions of the step per second per cubic meter, if they weren't equal in equilibrium, or if they're not equal to one another, we couldn't be in equilibrium, because we would be causing some reactants to be either being consumed faster than they're being made, or vice versa. And so we then talked about how if somehow we had equal amounts of helium-3 and deuterium per cubic meter, equal numbers of deuterium and helium-3 per cubic meter, then the fact that, if we call this 1 and this 2, the fact that, so which one of these happens faster? Is it that the deuterium nucleus finds a proton and becomes a helium-3, or is it that two helium-3s find one another and become helium-4? You remember, what about the lifetimes here? How long does the deuterium last before this happens? How long does the helium-3 last before this happens? Roughly speaking.
Helium-3 lasts for a very, very long time, thousands of
Yeah, like 400,000 years or something like that, or yeah, I think it was like 400,000 years is how long one typically spends before it smacks another helium-3. Deuterium, just like that. Deuterium is very reactive. And so if you had equal concentrations, well, this would be happening much faster than this. deuterium would be being used up and converted into helium-3 much faster than helium-3 was being converted into helium-4. And so if you had equal amounts, the deuterium concentration would drop, creating more and more helium-3 as a result of that. So that couldn't be an equilibrium situation, having equal amounts of deuterium and helium-3. The fact that one happens much faster per reaction than 2 would mean that the deuterium would rapidly be converted into helium-3 until there was so little deuterium compared to helium-3 that the conversions would proceed at equal rates. You need a lot more helium-3 around to have the same rate of it disappearing as deuterium, because per reaction it's so much harder to make helium-3 disappear, that the conversions would occur at equal rates. Producing equilibrium. Does that make sense? Because, I mean, I'm not guaranteeing I'll ask you this on the exam, but I sure might be tempted to ask you to explain, well, how come in the sun's core there's a lot more helium-3 nuclei per cubic meter than there are deuterium nuclei per cubic meter? The answer is that if that wasn't the case, the deuterium would be rapidly converted into helium-3 because it's so much easier to do that than it is to convert helium-3 into helium-4. And so, in other words, when you have a reaction that proceeds quickly versus a reaction that proceeds slowly, the concentrations, the number of nuclei per cubic meter, is going to be a lot higher for nuclei where their conversion is a lot slower, because you need more of them around to get the same number of reactions per cubic meter per second. What questions do you have? Including, could you say that again? What? So could you explain that? Could you explain it? Putting you on the spot here. Getting there, okay? Do you need any further help getting there? Or are you just thinking about it?
So, the step that's more.
Yeah, so the idea would be that there will be a lot, if you have, consider some cubic meter of the sun in the core where these nuclear reactions are happening. For the amount of helium-3 to remain steady, what you would want is the rate at which deuterium is making helium-3 per cubic meter, the number of new helium-3 nuclei being generated every second per cubic meter, should be the same as the number of helium-3 nuclei that are disappearing because they're turning into helium-4 per cubic meter per second. In equilibrium, if you want the helium-3 concentration, the number of those nuclei per cubic meter to stay constant, there has to be just as many being destroyed as there are being created. And the point here then is, well, now consider the deuterium. Well, same deal with the deuterium. You need to have the amount of deuterium being destroyed every moment, being the same, a second, being the same as it's being created. And if you look at this pair of reactions right here, if there were just as many deuterium nuclei in every computer, every cubic meter, as there were helium-3 nuclei, well, deuterium disappears quickly. Any given deuterium nucleus isn't long for this world. It very quickly disappears. And so what would happen is that, wow, deuterium is rapidly being turned into helium-3. And that would mean the amount of deuterium was diminishing and the amount of helium-3 was increasing. So they couldn't have the same concentrations. That would not last long. But over time, there'd be less and less deuterium and more helium-3, so that eventually there was so much more helium-3 around that even though any given helium-3 takes a long time to turn into helium-4 to be destroyed, there's so many of them around that even though any one of them is going to take a long time for it to be turned into helium-4, there's so many around that there's always enough being turned into helium-4 every second to make up for how many are being created by deuterium being combined with a proton every second. So reactions, so if you have a reactant which it's hard to destroy, so to speak, or create, there's not going to be there's going to be a lot more of that around to compensate for the fact that any one of them takes a long time to be destroyed, so you need more of them around to get the same number being created every second, essentially. That's the big picture there. And again, it's always an average, right? Yeah, on average, it's going to be 400,000 years or whatever it is for a helium-3 to go away. But that's just an average. There's always going to be some that are going to go a second from now. But to have a significant number of them, there better be a lot of them around so that you can have enough of them beating the average like that so that you can keep everything in equilibrium. That's my long-winded explanation again. So that's the idea there.
So concentration-wise, there should be more helium-3.
There should be more helium-3. That's right. There should be a lot more helium-3 because you need a lot more helium-3 around. Since each one isn't very likely to, another way to put it is that if it takes on average 400,000 years for one of them to fuse, then that means that for a given number of helium-3 nuclei around, the longer the lifetime of a helium-3 is before it fuses, the fewer reactions per cubic meter are going to be happening for a given number of those nuclei. So in order to compensate for that, you have to have lots and lots of them around to get the same number being destroyed every second as they're being created by the deuterium, which is a much easier thing to do. Okay, that's so think about that, and that's the idea. Okay? Can we proceed onward at this point? All right, let's do so. Okay. So this all, can I erase this stuff here? No! Okay, I cannot erase this. Okay, then I'm going to start writing underneath here. Continue along here. But you're wanting to write that?
Just keep on.
Okay, keep on writing here. And I'll just do it. No, I will not do it again. It's up here. Sorry. Unless somebody really offers me a lot of money for it, but I don't think it would be worth it. You would not be getting this money. He was just talking about, we were this workshop, and they were talking about how, like, some students, it causes them a lot of anxiety to do public speaking. How do you deal with that? Maybe some students are so anxious about public speaking, oh my God, they just can't do it, so you let them record their talk. But you really want to encourage them to actually do the public speaking because exposure helps you overcome that fear, and it can be good to be able to do public speaking. And then somebody brought up like doing karaoke. That's where I would draw the line. Nope, not gonna get me to do, I can do public speaking, public singing is not gonna happen. And that's for the good of everyone involved. So, only my wife gets to hear me sing. Other than that, nope, okay. Except back on the Japan trip in 2010 where, yeah, students actually got me into a karaoke room and they made my wife and I sing Don't Stop Believin'. And I told them if I ever see the videos y'all are taking anywhere on the internet, I will track you down. I never did see them, don't know that they're not there, but in any case. All right, can I erase it? Anybody stopping me here? Okay. All right. So, okay, so, thus, we can rewrite this as epsilon is equal to available energy generated per the whole reaction series all the way to the end. So for example, with the proton-proton chain, this would be like sum up the whole thing, that when all is said and done, 4 protons become a helium-4 nucleus plus, we'll kind of summarize with energy right there, the available energy there. Even though this has multiple steps, the whole reaction series can be summarized as 4 protons become the helium-4 nucleus plus energy times the number of reactions of any one step per cubic meter per second. Because they all happen at the same rate. And so, because all the steps are happening at the same rate, then the whole reaction series you can think of as is happening at that rate per cubic meter per second, because the whole every step in the series is happening at that same rate. So effectively, the whole series itself is happening that same number of times every second, and then we're still multiplying by the number of cubic meters per kilogram. What questions do you have?
What does it mean to divide by like the whole reaction series?
Oh, don't think of that as a division here per se. What I really mean by that is per whole reaction series. So in other words, how much energy is generated every time the whole reaction series goes through. That's in that sense. It's like a symbolic division. It really means every single time the whole reaction series goes through, how much energy got generated in total. That's what thanks for asking. Yeah. Any other questions? Yes?
So that is, let's say for example, how much deuterium is being converted to helium-3 in the sun, in that sun.
So this is, we could write out the whole proton-proton chain, PP1 chain, all 3 steps of it, for example, right? And each step produces a certain amount of energy. And the total amount of energy that's generated is the sum of the energy that each step produces per reaction. And that is what appears here. You add up the total amount of energy from all the steps together. And since they're all happening at the same rate, all of the steps are happening at the same rate, then we can think of then, instead of having to write that out all separately, how much of this reaction is how much of this step is happening times how much energy it's generating and all that sort of thing. Everybody's happening at the same rate, and so therefore I can just say, okay, well then the whole sequence is happening at the same rate that any one step of it is. And so then I can just turn that into, okay, how much energy am I getting from the whole sequence per cubic meter per second? How many times does the whole sequence have per cubic meter per second? Because that's the same as how much does each step happen per cubic meter per second. And then I add all the energies together. So it's okay. All right, so now, if nuclear species I and X, and that's just the name your book gave them, so that's why I'm choosing I and X as their name. We're kind of thinking like I, meaning you've got two nuclei, they're going to smack into one another, and you kind of think of one as the incident one, and one is like the target one. And so I sort of stands for incident, and X stands for target because there's no X in target, and so why not use that? Yeah, I don't know. So if nuclear species I and X are involved in some particular step in the reaction, some particular step of the reaction sequence, then we can write the following. So tau sub I inverse, where what that means is tau sub I is the mean lifetime of species I. So for example, and I should look it up to be sure, yeah. So e.g., in other words, that was 400,000 years for helium-3, as that example we've been using. How long on average that nuclear species lasts before it undergoes a reaction? Any given nucleus of that species lasts before it undergoes a reaction. Of course, we convert that into seconds. And so a lifetime, how long a species lasts on average, the reciprocal of that would be how many reactions per second. In other words, the lifetime is how many seconds per reaction, so its reciprocal is the rate, the number of reactions per second for that species. Tau I inverse is equal to the number of reactions per second per nucleus of type I, which is going to be the reciprocal of how many seconds per reaction of that nucleus. Well, that should be proportional to, I like to call that the proportion fish. That should be proportional to the number of nuclei of type X, the ones that it's interacting with, per cubic meter, and the number of nuclei type X per cubic meter is what we would call N sub X, the number density of species X. How many of those nuclei are there per cubic meter? In other words, the more targets are available, the more target nuclei that are available, because species X is the target, if you will. Species I is looking around looking for species X to interact with. So if we think of species I as the incident nuclei and species X as its target, the more target nuclei that are available, the more reactions there will be per nucleus of type I. Right, so, you know, it's kind of like, imagine that you really like to go up and shake hands with people who are wearing blue shirts because you're kind of weird, okay? You really like to go up and shake hands with people who wear blue shirts. And so there you are in Grand Central Station, and you're going to go around and try to find somebody to shake hands with because they have a blue shirt on. Well, the more people that are walking around with blue shirts, the less time it's going to take before you find somebody to shake hands with. That's the basic idea here, right? The more targets there are around, the more nuclei are around that you want to interact with, because you have nothing you desire more than to have a nuclear reaction with the nucleus of type X. The more of them are around, the less time it's going to take for you to have that interaction. And therefore, collectively, if there's lots of you around trying to shake hands with blue shirt people, there's going to be a lot more handshakes with blue shirt people every second if there's more blue shirt people walking around. If you're a nucleus of type I, you're going to have collectively more nuclear fusions with nuclei of type X per second if there's more nuclei of type X around in every cubic meter available for you to potentially have nuclear reactions with. Does that kind of big picture there make sense? Okay? So, number of reactions per cubic meter per second is going to be equal to number of nuclei of type I per cubic meter times number of reactions per second per nucleus of type I. Right? If a given nucleus of type, if there's a given nucleus of type, what am I trying to say? A nuclei of type I, the number of reactions per second per nucleus times how many nuclei there are in every cubic meter will be the total number of reactions per cubic meter per second. And that will be proportional to, well, over here, we said there should be a proportionality to the concentration, the number density of type X, and this beast right here, right, so this was going to be proportional to Nx, and this piece right here is N sub I, so the whole thing is proportional to N sub I, N sub X. So collectively what this is saying is that if people with red shirts really like shaking hands with people with blue shirts, then it's collectively true that the more red shirt people there are around and the more blue shirt people there are around, those both are going to increase the reaction rate. If you double the number of red shirts around, twice as many handshakes every minute or second or whatever in the train station. If there's twice as many blue shirts around, twice as many handshakes per minute. If you double them both, 4 times as many handshakes per minute. That's kind of the big picture here. I did not go in thinking I'm going to talk about handshakes between people with different shirt colors. But I'm just going with that. That's just what hit me as we were going along here. Just in time teaching, I guess. I don't know. Anyway, what questions do you have? Okay, so now we're building up to setting up one of the homework problems here. Excitement here, okay? In fact, we can be more specific here. RIX, which is defined to be the number of reactions per cubic meter per second is equal to NI NX. We said it was proportional to what's the constant of proportionality. It's going to be this thing which I'll define after I write it. It's going to be angle brackets sigma v sub ix. Which, okay, what the heck is that? Well, I have to say what the heck that thing is. Where, and as soon as you see it, you'll say, oh, well, that's obvious. Actually, you won't, but, and then we'll have to show why it's true. Where angle brackets sigma VIX, it's kind of like in a sense, like an average value, so to speak, an expectation value of sigma V. Why, this is the integral from 0 to infinity of cross-section as a function of energy. That's what the sigma stands for. Cross-section, what's that? We've sort of mentioned that before. It describes how easy it is for interactions to take place. Well, we'll give it a precise definition. The reaction cross-section as a function of energy times V as a function of energy, particle speed as a function of energy, times P of E dE. So it's this integral we have to calculate. So let's write out what the definition is of each term in that integral. So here, sigma of E, sigma as a function of E, is the reaction cross-section of a function as a function of energy in the center of mass frame. And again, we'll give a precise definition of what reaction cross-section means. It shows up in particle physics and nuclear physics, both. So reaction cross-section as a function of energy of the interacting nuclei, the ones that are looking to smack into one another and fuse, of the interacting nuclei in the center of mass frame, in our center of mass frame. So any pair of nuclei approaching one another jump into the center of mass frame and find their total kinetic energy in that frame. V as a function of E, well, that's going to be the square root of 2E over the reduced mass. That's the center of mass frame relative velocity as a function of energy. because how can we write the total kinetic energy in terms of the reduced mass in the center of mass frame? It's as simple as saying, what is the formula for kinetic energy in terms of speed? Kinetic energy equals what times what times what?
1/2 mv squared.
Yeah, 1/2 mv squared, but since we're in the center of mass frame, we can do the equivalent one-body problem business of 1/2 mu v squared. Remember that we showed way back last semester that if you have two particles coming in, their total kinetic energy would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But if you jump into the center of mass frame and use the equivalent one-body problem, then you can just write that as 1/2 times the reduced mass times v squared, where v is their relative velocity, how fast either one is moving with respect to the other one compared to one another. That would be the speed of the reduced mass in the equivalent one-body problem. So 1/2 mu v squared, okay, solve for v, and you get 2e over mu m is v squared, take the square root. Root 2e over mu m is the relative velocity, how fast they're moving in the center of mass frame, how fast they're moving relative to one another, which is the speed of the reduced mass in the equivalent one-body problem. Does that make sense? What questions do you have? And that's just Newton speaking to us here. What are we assuming about the motion of the particles here? What is the speed that they're not moving close to for us to get away with that formula for the kinetic energy? They're not moving near the speed of light. Yeah, they're non-relativistic. We're assuming that they're non-relativistic here. Otherwise, we'd have to use the relativistic formula for kinetic energy. And then P of EdE is the probability that a particle has energy in the range from E to E plus dE, right, which we'll write as like the interval E comma E plus dE, a narrow range of energies between E and E plus dE, according to the Maxwell-Boltzmann distribution. According to the Maxwell-Boltzmann distribution, so here's one place where a homework problem comes in. And that is, in the homework, you will show, how will you show it? How does one always show these things in homework? You will, it starts with a J.
Joyfully.
Yes, you will joyfully show, right? It's important to put this out. You will joyfully show, can't leave that out. You will joyfully show that P of EdE is equal to 2 over pi to the 1/2 power times kt to the 3/2 power, still down in the denominator, e to the 1/2 power e to the minus e over kt V hint. And what's the approach here? Because the homework problem just says, show this, and you might be like, what? So let's talk about what that means. So, the Maxwell-Boltzmann distribution, remember, is a plot such that P as a function of V dV is probability that a given particle, which in this case would be like the reduced mass of the system, that a given particle has speed in the range from V to V plus dV. And so if I plot the Maxwell-Boltzmann distribution, it looks something like that. I just made a rough sketch there. And so here is a little narrow range of velocities where it goes from V to V plus dV, and I'm being committing the typical physicist slash astronomer sin of saying, well, here's my V-axis, and this is V, and this is V plus dV. So, okay, yeah, it should be like, so I shouldn't really use the same notation. I don't care. I think you know what I mean. So here's some value of V, here's a value a little bit dV larger, and so P of V dV is essentially the area of this little rectangle right here, or parallelogram, or whatever you want to call it, right? So area of, it's really, think of the trapezoidal approximation when you're doing an integral. Area of that little trapezoid slash rectangle, if we want to be, because this is really the formula for the area of a rectangle, P of V times dV is P of V dV. It would really be the area of that little rectangle right there. But as the rectangles become smaller and smaller, you're making the Riemann approximation for the integral, blah, 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 blah. Y'all know what I'm talking about? Is that making sense, that basic idea there? Okay. That's so P of V is the probability density, the probability per unit velocity interval that you'll find a given particle with its speed in that range according to the Maxwell-Boltzmann distribution. And I don't have the notes with me for it. There's some normalization. It's blah times e to the minus mv squared over 2kt 4 pi v squared dv, where I forget what blah is, but you'll look it up in your notes or the book and you'll use it in doing the problem. And so we can already see part of what's going here. And if we're doing it in the center of mass frame, we would just put the reduced mass there instead and say e to the minus mu sub mv squared over 2kt. What is mu sub mv squared over 2? That's the energy, right? So that's why there's e to the minus e over kt. That's just writing e to the minus mu mv squared over 2kt in terms of e. There's the e to the minus e over kt term right there. And, okay, what about the rest of all this? The key is that if we switch from V to E as the variable, and let E to to E plus dE correspond to the range B to B plus dB. Then the same particles are involved, if you will. In other words, if you have a box of particles, and you say, how many are in the range from B to B plus dB, which would be the number density times the probability that any one of them is, well, now if you just switch things and say, okay, what energy corresponds to B, and what dE corresponds to dV, it's really the same particles, you're just talking about them in terms of the range of energies they span instead of the range of speeds that they span. Then the same particles are involved if we are considering some population of them. Right, so again, P of EdV is the probability that a given particle has some speed in that range. So number of particles per cubic meter in the range from, get too short on the chalk here. It's time to switch to my glorious new chalk here. In the range from B to B plus dV, the number of particles in that range would be equal to n times P particles per cubic meter in that range, would be n times P of dV, because what does n represent? What is n? It's a number density, so it is the what was all that? And the number density is the yes.
Number of particles of that species in
per cubic meter. Yeah, that's the number of particles per cubic meter. So total number of particles per cubic meter times the probability that any one of them is in that range of speeds would be how many are in that range of speeds per cubic meter. If then we just say, okay, what energy corresponds to V, and what energy corresponds to V plus dV, and call that energy E plus dE, if that's a corresponding range, the corresponding range of energies for that range of velocities, it's the same particles we're talking about, and so it must be the same number per cubic meter, so we can say that P of V dV is equal to P of E dE, where those B's and E's correspond to one another, and the dV and the dE correspond to one another. What range of energies corresponds to that range of velocities? Does that make sense? That's what I'm trying to drive home here, is we're talking about the same particles. We're just saying it's a certain range of energy versus a certain range of velocity, but it has to be the same one. Like if the velocity is between 1,000 meters per second and 1,001 meters per second, you could calculate, okay, well, what energy corresponds to 1,000 meters per second? What energy corresponds to 1,001 meters per second? And now just talk about how many particles are in between those two energies. Or in other words, this says that P of E, the thing that you're looking for, right? This is P of E right here. This all is P of E. That is equal to P of V times the derivative of V with respect to E. And that says, everywhere you see a V, substitute, what is it? V is square root of 2e over mu sub m, or you could just call it m if you wanted to. But we'll call it mu sub m because we're supposed to be in the center of mass frame here, right? So, and find this derivative and write it in terms of E. And when you do so, if you don't get this as the result, you did something wrong, is what it comes down to. So that's what you're supposed to do there. Quick time. Yes. I mean, it's a little roundabout.
Especially when you're talking about new reactions.
Yeah.
Yeah, right.
Yes.
Well, this for financial decisions, more they're just gonna afford it.
Okay. So now let's answer why it should be that that integral we wrote down should in fact represent that integral times ni and x should in fact be the number of reactions per cubic meter per second. And so again, you know, if you ever get interested in particle physics or nuclear physics, go back to these notes because this is exactly the sort of things they talk about. Really, in chemical kinetics would have this sort of thing involved in it. But what's a cross section? We've used the word many times. It's like an effective area. It does in fact have units of area. Cross-section is defined as follows. The cross-section, sigma v, by definition, triple equals, by definition, it's number of reactions per target nucleus per second. Right, the X is there. Number of reactions per target nucleus per second divided by the number of incident particles. Actually, I'll say nuclei because it's nuclei that are incident here. In general, if we're doing particle physics, it would be target particle, incident particle, but we're talking nuclei here, so we'll put it in terms of nuclei. Number of incident nuclei per square meter per second. That beast on the bottom is what we call F, the incident flux. This is for a beam of incident nuclei I. Incident nuclei, the ones we're calling I, directed at a target nucleus X. And it's sigma v here. If we got rid of the E, if we just said sigma in general, would be add this up for all possible energies. It's sigma v here where we're assuming all the particles have energy E. here we are assuming all the incident particles have energy E. They're all coming in with the same energy, therefore the same speed. So in other words, it's kind of like, you know, I'm the target nucleus, and y'all are a bunch of incident nuclei, and here I am, and let's see if any of you bump into me. And so y'all are coming towards me, walking towards me, and imagine you can fly. And so we're in outer space, and you're all flying towards me. And the question is, how often do I get smacked by somebody flying in towards me? So the flux would be how many target particles, target people, are there coming through per square meter per second. So like draw 1 square meter area. Actually, people aren't going to fit very well. So here I am, and y'all are going to throw, I don't know, marbles at me. And so you send this beam of marbles at me. And the incident flux would be, take a square meter around me here. How many marbles are flying at me per square meter per second? That's what we mean by the flux. So the more concentrated that those marbles are, the more are coming through a square meter per second, the more they're going to hit me. And furthermore, the bigger I am, the bigger the cross-sectional area I present to all those marbles, the more they're going to hit me every second. And so the cross-section here is defined to be the rate at which marbles are hitting me, or you if you want to be the target here, the number of reactions per target nucleus per second divided by that incident flux. And the bigger, this is look at the units of this, right? In other words, we've got reactions per target nucleus per second, incident nuclei per second, everything cancels in terms of the units, except we've got 1 over meter squared on the bottom. And so therefore the units are in fact meter squared. The units are area here that we're talking about. So the cross-section represents area. And in fact, if you think of a little hard sphere, think of a hard sphere target there, and you think of, here I'm drawing a bunch of incident particles coming in, and to keep it simple, they'll just be little point particles. We talked about something similar to this before when we were talking about like absorption and so forth, absorption, scattering, and all of that. If we call the cross-sectional area of that hard sphere, we're representing like the nucleus as a little hard sphere. It's like imagine it like a little billiard ball, so to speak, in a mental picture, and you're shooting little tiny particles at it. And the question is, how many of them smack it every second? There's a hard sphere of target cross-sectional area A. So in terms of its radius, what would sigma be? What's the cross-sectional area of a sphere? Just to be sure you know what I mean by cross-sectional area. That's why it's called a cross-section. Yeah, pi r squared, right? Because it looks like a circle. to the incoming particles. It doesn't really matter that it's really a sphere with area 4 pi r squared. What they see is a circle of area pi r squared. So it's the cross-sectional area that matters, right? If F incident, and then let's assume that this is 1 meter by 1 meter. There's a 1 meter by 1 meter area. Why? What's its total area then? It would be 1 square meter. Did I push the button on that?
Yeah.
Did I? I did, okay. I couldn't remember all this stuff. Okay, so if F incident particles come through 1 square meter every second, a fraction, what fraction of them hit the target? Well, if they're just randomly distributed, and this has and this target has area sigma, and there's F particles randomly distributed over that square meter coming through every second, what fraction of them smack the target and thus interact with it?
Sigma over meter squared.
Yes, sigma over 1 meter squared. Then a fraction sigma over 1 meter squared will hit the target. So, number of hits, interactions, if we're thinking of these representing, they get to fuse if they're nuclei. Number of hits per second per target nucleus will be equal to sigma over 1 square meter times the flux. Times the flux. So that's why sigma is defined the way it is. Number of reactions per second per target nucleus over F should be equal to sigma. So that's why we define sigma like that. But this lets us generalize to when the target is a quantum fuzzball. So to speak, right? In other words, nuclei aren't really little hard spheres and you either hit them or you don't. They're quantum fuzzballs, and you have a certain probability of interacting with this quantum fuzzball if you're a particle coming in. And so we can still make the same definition, and so sigma just becomes what area of a hard sphere would produce the same reaction rate as our actual quantum fuzzball does, where there's just some probability that's going to depend on how close they approach one another and so forth of them interacting. We can just generalize to, okay, well this ratio is always what we call the cross-section, and it's the effective cross-sectional area that the nucleus is presenting to the incoming particles, so to speak. And this shows up in particle physics all the time. You talk about cross-sections all the time, and that's the idea here. The particles are really quantum fuzzballs that might or might not interact with one another with a probability that depends on how close they come to one another in the quantum fuzzball way. And we can refer it back to a model of little BBs trying to hit a hard sphere, where you naturally define the actual cross-section of the hard sphere as being what determines that. Take the same ratio and call that the effective cross-sectional area for the interaction, and that's what cross-sections are. You can even get more fancy and talk about the differential cross-section, and then to say how many, if it's a scattering event, how many scatter per unit solid angle as a function of angle of scattering per incident flux. So you get even fancier. So particle physics, you make theoretical calculations of what you call the differential cross-section, and then perform the experiments and see how well you do. Anyway, we're just interested in the total reaction. What questions do you have? And erase this side of the board, the far side there. Now, if it was really just hard spheres, you wouldn't particularly care what the energies were. If it's just a matter of if you hit the sphere or not. But with quantum fuzzballs, how probable an interaction is can depend on how energetic the particles are and so forth. So sigma in general is a function of the energy. Now, for particles having speed v, F is equal to V is a function of E times N sub IE dE is the flux of particles in energy range from E to E plus dE. So why should this be? Okay, I'm going to draw myself a fancy rectangular parallelepiped. So there we go. And then here's the hidden surfaces there, also known as a stick of butter. Right, so, okay. That's supposed to look nicer than that. But there's my stick of butter, so to speak. It's a rectangular, it's a volume of space. What volume of space is it? So, N sub IEDE is the number of incident nuclei per cubic meter. In the range of energies from E to E plus dE. So in other words, N sub IE is the number of particles per cubic meter per unit energy interval times the width of the energy interval will be the number of particles per cubic meter that are flying towards our target nuclei. So I'll just kind of, here's a bunch of particles of type I. These are all type I particles. There they are, flying along. And I'm drawing them all as having exactly the same speed v. I'm trying to make all those arrows the same speed, the same length. Those little velocity arrows. They're all moving the same speed because I'm considering this narrow little range of energies. And I'm going to say that this is 1 square meter. In other words, before I drew this here, here's my square meter, and here's all these particles coming in. My rectangular parallel pipette is sticking out of the board towards us here, and we are looking, we want to know how many of these particles are passing a square meter every second. Well, the idea would be, okay, here they all are flying through a square meter at the front here, and let's say they're all moving with speed v. Root T 2e over m. In 1 second, how far do they fly? If they're moving at speed v, how far do they fly in 1 second? Yes, that's right. They fly v meters in 1 second, right? So this distance right here is v times 1 second meters. V for vendetta or something. So, okay. So, you know, like what if these are a bunch of icky flies or something like that? And there's all these flies swarming towards you. If there were n flies per cubic meter, then if you considered a 1 square meter cross-sectional area and a bunch of flies moving at speed v everywhere, how many pass through a square meter every second? Well, the volume that passes every second is 1 square meter times how far the flies move, which is their speed times 1 second in meters. If this were a continuous fluid, we'd be talking about what volume of, say, water passes through each square meter every second. If there's fluid flowing down a square pipe, then the volume of fluid that flows past any cross-section of the pipe is the area of the pipe times how far the water moves in 1 second. It's speed times 1 second. So that area times the speed times 1 second would be how much volume of water passes through each square meter in 1 second. So the volume of the rectangular parallel pipette what's the volume of that rectangular parallel pipette? How many cubic meters is it? Yes, V for vendetta, right? Because it's 1 square meter times V times 1 second. So it's V cubic meters, the volume of V cubic meters of volume of incident particles, if you will, passes through the front face every second. Every second. And so that's why the flux, the number of particles per square meter per second, is V cubic meters times every second times the number of particles per cubic meter in this little area, energy range. Number of pi particles per cubic meter in our little narrow energy range, number per cubic meter times volume volume per second passing through each square meter will be the number of particles per square meter that are incident. That's the idea there. So we're calculating how many incident particles pass a square meter every second. It'll be NIE, the number per unit volume, times V, which is numerically the amount of volume that they sweep through that surface every second. I hope that's clear, and if it's not, tell me. This is good fluid mechanics thinking here in general. This is the kind of thing you have to think of, like a flow in a pipe. How many kilograms of water flow through a given cross-sectional area of a pipe? Well, it would be the volume of water that flows per second through the cross-section times the density of the water. And we're doing exactly the same kind of calculation here. The speed times 1 second is the length of water that flows through a cross-section of the pipe, multiplied by that cross-sectional area, and that length times that area is the volume of water that flows through 1 second through the cross-section of the pipe, multiplied by that by the density, and that would be how many kilograms of water per second are flowing through the cross-sectional area. Or if we're talking particles, it's how many particles per second are flowing through that cross-sectional area. So think about that carefully. What questions do you have? Including, I'm not even sure what the question is. I can't tell. People are like, I have no idea what you're talking about, Dr. Harmon. Where are we with this? Anybody want to be bold enough to say, what? What? Are you being bold enough to say what? Yeah, that's fine, that's fine. If you are.
I'm almost there.
Almost there. Almost there.
I can still say what.
You still say what? Yeah. But I want to know if it's what as it means I should say something. Yes?
When it says over there, like the number of reactions per second per target nucleus, is that saying like for each target nucleus?
Yes, for each target nucleus, how many reactions are there per second? Yes. Now, if it's a fusion, it stops being a target nucleus once there's a fusion. But you'd still think of it in terms of, okay, well then that would be the reciprocal of how long on average does that nucleus live. I can't tell if I should keep talking or not, or just think about this and then ask me later or something. Okay, so I'm going to keep going, and if you're still puzzled, you're going to spend quality time with me talking about this some more. Okay? So, then, this is the kind of thing that rewards careful, deep thinking about it. It's also the kind of thing where, especially when I was first learning this, I'd be like, I got it! And half an hour later, wait, what? Oh yeah, I got it! And then an hour later, what? I got it! And then 2 hours later. Eventually it was longer and longer before I stopped counting it. But it's the kind of thing I thought about over and over again until I really got it, so to speak. Okay, then number of reactions per target nucleus per second, which we keep wanting to know here. Reaction rate is sigma of V NIE, sigma of V, V of E, dE, because sigma times the flux is the number of reactions, and so the flux is V NIE dE. So sigma V NIE dE is the number of reactions per target nucleus per kilobit per second. And that we can say is, sigma E, I meant to say. Could write it in terms of V, but we're doing it in terms of V. Sigma of E, V of E, and then, well, NIE will be the total number of nuclei of type I per cubic meter times the probability that any one of them is in that narrow energy range dE. And P of EdE is that probability. Total number per cubic meter times the probability they're in that narrow energy range dE is NI dE. If there's a 1 in a trillion probability they're in some narrow energy range, and there's 10 to the 24th of them every cubic meter, then there would be 10 to the 24th times 10 to the minus 12 equals a trillion of them in that narrow energy range per cubic meter, for example. So total number per cubic meter times the probability any one of them is in our little narrow range will be the number that are in our little narrow range of energies per cubic meter. Now, we multiplying this by the number of target nuclei per cubic meter, and integrating over all energies, add up for all energies, these probabilities, these reaction rates, integrating over all energies, 2, 4, 6, 8, time to integrate, so it doesn't work out well, yields the desired result. RIX, number of reactions per cubic meter per second, for any one step in the sequence, but remember it's the same for the whole sequence because they're all in equilibrium. If they're all in equilibrium, it's the same for every step in the chain as it is for any one of the steps. Number of reactions per cubic meter per second will be NINX times this integral 0 to infinity of adding up the sigma of E, V of E, P of E, dE. As claimed long ago, such that you've probably forgotten what we were trying to show. But this is what we were trying to show, is that that should be what RIX is equal to. And again, I will say, I will not at all be surprised to find that you didn't follow every step of this fully. This is the kind of thing where talk to me one-on-one, because if I talk to you one-on-one, I can work with you and figure out how I need to explain it to you to get you to understand it. It's hard to find just the right way to explain to a whole room full of people all the steps of this. It can be something where it's very helpful for me to talk to you one-on-one about this, because everybody has a somewhat different way of understanding things, so I can try different things. So I highly encourage you to keep me from crying from loneliness in my office. I like talking to people in my office. And you can eat my candy too. And keep me from eating my candy, which is a valuable thing. That's always the problem with a candy bowl. I see it too. All right. Okay. In my notes, this is where I say, as a homework problem, you'll show, I didn't put joyful, anyway, about what P of EDE is. So we already covered that. We'll show that in the homework. Now we say, it is useful to factor out the predominant energy dependencies of sigma of E. Predominant energy dependencies of sigma as a function of E. And so, as the book says, sigma of E, we define it to be capital S of E, which we'll say more about in a minute, times what we're going to say is the effective cross-sectional area times. So remember that for there to be a nuclear fusion, they have to tunnel. So there's going to be times the probability of tunneling. Probability of, the book says, barrier penetration, by which we mean tunneling. What's the probability that they, find each other and fuse? Because classically, remember, they wouldn't do it because they wouldn't get close enough to feel the strong nuclear force and fuse because of that attraction. But quantum mechanics says, no, even though classically they couldn't get close enough, in quantum land, there's some probability they'll sort of accidentally find themselves effectively close enough. So where S of E equals a, we hope, and usually this dream turns out is fulfilled, we hope, slowly varying function of energy that accounts for the gory details of the nuclear physics. So we leave this one to the experts, to our nuclear theorists. Here be monsters. But it turns out those smart nuclear physics types, right, because that's one of those things that has a reputation, right? Nuclear physics, right? Brainiacs or whatever, right? So it turns out that it's mostly this effective cross-sectional area times the probability of barrier penetration times something else that doesn't change a lot, and is the idea there. And so this is, we're waving the chicken feet here. It's like, take my word for it, and I'm taking the nuclear physicist's word for it. That it works out that for the most part, there can be what are called resonances, where S of E has spikes. But for the most part, it doesn't change much with energy. It's mostly these last two terms there. So wait, what is this effective cross-sectional area of which you speak? Well, let's write that out. What's that? And we're still waving chicken feet here. This is again, okay, this is what the smart people find out here. So the effective cross-sectional area well, that's pi lambda squared, where that's the de Broglie wavelength, de Broglie, or whatever you say, That's the de Broglie wavelength. Pi lambda squared. So in other words, they kind of look like the radius of the sphere is the de Broglie wavelength, the quantum fuzzball, if you will. In terms of the particle's momentum, again, it's really the reduced mass. What is the de Broglie wavelength in terms of the momentum and Planck's constant? Remember, lambda is what? Over.
Pure ridge.
What's that?
It's pure ridge.
Over.
Other way around.
Okay, yeah. Over. Broglie wavelength is h over p squared. Well, that'll be pi h squared over 2 reduced mass e. Because remember that E is, right, we say E is 1/2 mu v squared, but it's also p squared over 2 mu. Right? And remember, I've said it before, in some ways it's better to think of kinetic energy as p squared over 2m as opposed to 1/2 mv squared. They're both the same thing, but momentum is more fundamental than speed is. And so p squared over 2m, that's 1/2 m squared v squared, or sorry, it's m squared v squared over 2m, right, which is half mv squared, u if you use the u's method. So that's why we can say that 1 over p squared is 1 over 2 mu e, like p squared is 2 mu e, in other words. And so it goes like 1 over e is the point here. The effective cross-sectional area is proportional to 1 over the energy. The energy dependence is 1 divided by the energy. A detailed quantum mechanical analysis wave the chicken feet. Right, so let the smart people do that. Shows that the probability of barrier penetration, the barrier penetration probability, goes like e to the minus 2 pi squared u sub c over e, where u sub c is the height of the Coulomb barrier for R equals lambda equals h over p. In other words, the height of the Coulomb barrier when they're a de Broglie wavelength apart from one another. So h over mu v. So uc plugging into the formula for the Coulomb barrier is going to be Z1, Z2, E squared, right? Because the two particles are Z1E times Z2E in charge. And remember, the Coulomb potential energy is Q1, Q2 over 4 pi epsilon naught R. So put in H over P for R, and that'll give you Z1, Z2, E squared over, times mu V over 4 pi epsilon naught H. Just plug in the de Broglie wavelength H over mu V for R in the Coulomb potential energy formula. Note that UC increases as V increases. So the barrier is actually getting taller as E increases, which in and of itself would make for harder to get over it, if you will. But at the same time, we got closer, and so it's easier to tunnel through if you are closer. And therefore, UC over E is UC over 1/2 mu V squared equals 2 Z1, Z2, E squared over 4 pi epsilon naught HV. And so this is saying that E increases as V squared, because it's 1/2 mu V squared, or faster than UC does. So UC over E decreases as V increases. All right, and I'm sorry to do this to you, but you're just going to have to be in suspense. We'll just read the notes until next time, where we will come up with the idea of the very important gamma peak. And then in the homework, we'll joyfully show something about the energy at which the gamma peak appears, which is really just easy. It's taking the derivative of 0 and solving for E, which will do that. And yeah, and then that'll just be begging to have a question asked about you on the exam, but as you'll see, it's not too. Okay, so next time, and again, there's a lot here. I think we get all surprised. Somewhere along the way, you're like, wow, there goes Dr. Harmon, and I'm still on this place and over there somewhere. So come talk to me, is what it comes down to if you're puzzled with that stuff, because this is the kind of stuff where there's a lot in here, and I can work with you one-on-one to get you to understand all this parts. I could probably do that, yeah. Or at least, since I have to see exactly how far we get, but I can at least put up like, this chapter, for example, and then it'd be a, what's that?
How long do you think it'll take?
Yeah, I can just like, build it out in pieces, yeah.
15 minutes.
There you go.
Okay, I'll just
Everybody
kind of
wins.
number around like 4:30 then,
Yes.
I guess. I can text you. Text me when you're done. Dr. Harmon,
Yes.
the guy responded, I'm getting the accordion.
Oh, really? Oh, okay.
And I knocked $25 off.
And you knocked $25 off. Wow. Excellent.